So when most of us see a crack in a concrete bridge, we think defect.
Right. It's a sign of decay, maybe even danger.
But if you go through Dr. Oguzhan Bayrak's work in concrete bridge technology, you realize it's often the wrong instinct.
Mm,
His article, A Crack is Not a Crack, basically frames it like a crime scene. A crack isn't just a break, it's a map of all these invisible forces at play.
it really is forensic engineering, isn't it? Bayrak is pushing us to look past the visual what and really dig into the structural why,
And the main culprit in this particular story is torsion.
the twisting force, which is so much harder to diagnose than, say, just simple weight or bending.
Because you can't just see a twist, it's not like a sagging beam. So the article focuses on this specific setup, a straddle bend.
Which is that big cat beam you see sitting on two columns, usually over a road.
And the key here is that the load isn't centered. The north ledge is carrying a heavy load, and the south ledge is carrying a much lighter one.
Exactly. That imbalance is what creates the twist. It makes the beam want to roll over. Now, normally, an engineer is worried about shear,
The downward cutting force.
right, from gravity. But here you've got shear plus that twisting torsion.
Yeah.
And as Bayrak shows, they don't always add up cleanly.
This is where it gets interesting. He lays out scenario A, which he calls minor torsion. On the heavy side, the north face, the shear, and the twist are working together.
They're additive. They gang up on the concrete.
So you get that classic diagonal crack.
Yes. But then you walk around to the other side, the south face, and it's a completely different story. Shear's pulling down, but the twist is actually pulling up.
So they're fighting each other. Subtractive.
They cancel each other out. And this is the tricky part for an inspector, right?
Yeah.
You could have a beam under serious stress.
But the south face looks perfectly clean, pristine. You'd think everything's fine.
That's the trap. It hides the real stress.
Yeah.
But that all changes in scenario B, with major torsion. If that twisting force gets strong enough, it doesn't just cancel out the shear on that south face.
Yeah.
It completely overpowers it.
And that's where this idea of reverse shear comes in. The twist just wins the tug of war.
It wins, and it creates a crack that runs in the complete opposite direction of a normal gravity crack.
Wow.
And this is the real aha moment. If you could see through the concrete, you'd realize the crack on the north face and this reverse crack on the south face, they connect.
So it's a spiral, a continuous helix.
It's a spiral fracture wrapping the entire beam. If you see that reverse angle, you're not just looking at a heavy load, you're looking at a beam that is being wrung out like a wet towel.
So the direction tells you about the twist. But Bayrak goes further. He says the angle of the crack reveals something else entirely.
Axial forces.
Whether the beam is being stretched or squeezed.
This is the geometry part. Let's take a scenario D.
Yeah.
Imagine the columns holding that beam are just incredibly stiff. As the concrete shrinks while it cures, the columns won't budge.
That's restrained shrinkage. It's basically stretching the beam.
Yes, the beam is in tension. And when that happens, the cracks get steep. Much steeper than 45 degrees. That's your red flag.
It tells you the steel reinforcement inside is really having to work overtime.
Exactly. And the opposite is true for scenario E, which is compression.
So when the beam is being squeezed, maybe from post-tensioning cables.
Right. That compression literally squashes the crack. It suppresses its ability to climb vertically. So you see these much flatter cracks, less than 45 degrees.
It's amazing, a totally different diagnosis just from the slope of a line. And this feels so important because historically we just didn't think this way.
Not at all. In the 40s, the 50s, any diagonal crack was just seen as a failure. We used to chase every single one with epoxy.
But not anymore.
No. Modern codes, like the AHHTO specs, understand that cracked concrete can be a perfectly valid state. It can still transmit shear. A crack is often just the structure, relieving pressure so it doesn't fail.
It's adapting.
In many ways, yes. You have to look at the whole picture, the boundary conditions, before you decide if it's a problem.
So for you listening, next time you're under an overpass, don't just see a crack. Look at the angle. Look at the other side. Ask yourself, is there a helix of force wrapping around this beam right now? Is this structure actually failing or is it just breathing?